So first up, we're going to do a little introduction to differential equations and answering a good question. What is a differential equation? So as defined by DeMario, a differential equation is an equation that involves x, y, and the derivatives of y. So basically, you can look at the examples here. Any equation that has x or y in it, or a derivative, or x and y in it, that is a differential equation if it has derivatives in it. I want to make note of the fact that x and y, it is not necessarily referring to those variables. It just means an independent and a dependent variable. So this could be t and this could be p, you never know. I just note that. But a differential equation is basically an equation that involves derivatives. The solution to a differential equation is a function that satisfies the differential equation when the function and its derivatives are substituted into the equation. I'm going to go back to the idea of general solutions and stuff like that when we actually start solving these, but while we're just overviewing them and talking about them, I'm going to move into an example. So a solution, as just defined here, satisfies the differential equation, which basically means when I plug in a given function, such as this one, in this case, a lot of the questions about solutions are going to be like this, where we're going to test if the solution that they're giving us, if a proposed solution is truly a solution to the differential equation. And the way that we do that is by plugging in that equation into the differential equation and seeing if this equal sign holds up. So say you were to plug something in and you were to get something equal to 4 rather than 0. That would mean that the solution does not satisfy the equation. But in order to just solve this, which this is just a random differential equation that we're going to use to be able to just look at this topic real quick. Let me rephrase this. So we need to plug in this proposed solution into this equation, which it looks really easy to plug in the f of x there because f of x of x. But we've got this pesky little second derivative term here, and because that exists, we're going to have to take the derivative of this function twice in order to find out what that's equal to so we can plug it in. So we just have to do just that. So f of x is equal to, and this is chain rule, just for review sake, I'll write out chain rule over here. X. I'm going to put that 4. That's not bad. Ignore the 4. This is e to the x. It's going to be negative e to the negative x. So we're going to get a negative 4 e to the negative x. Then we can do this again, which is going to be the exact same thing. So we're going to get a positive 4 e to the negative x, because this is the same derivative, and that negative is going to cancel out this negative. So we have our two things. We have this thing and this thing. The two things that we have to plug in to see if the differential equation is true. So f double prime of x minus f of x equals 0. Our f double prime of x is 4e to the negative x. Oops. So 4e to the negative x minus f of x, which is here. Oh, ignore Connor. Anyway, that's our f of x. So we're going to plug in another 4e to the negative x. You might see where this is going. That's obviously going to equal 0 because it's the same term. And so that means that this is a solution to the differential equation given. So that one works out. There are going to be, actually, I think we have that next. Yeah, okay. Ignore my little blue markers. You'll see those a lot through here. I'm just checking that what I'm doing is actually right and I'm not just like lying to y'all. But anyway, which of the following is a solution to the differential equation y double prime minus 4y equals 0? So we want to find out which of these satisfy. So this kind of sucks. We have to do what we just did on that last problem for all 4 of these. So here we go. Y prime is, well, we want to just find double prime for all of these so we can see if that's true. So y prime is equal to 2 e to 2x. I'm not going to generalize just because it's going to be fine. And that's going to be 4 e to 2x. Now we can see we can plug in our y double prime, which is 4 e to the 2x minus 4 times y, which is just e to the 2x, equals 0. Now, if you look at this closely, that's going to obviously cancel out. It's the same, and so this is going to be true. So A is going to be one of our solutions. I think we have one more of these type of things, seeing if a solution satisfies the differentiable equation, but this is in a weirder way. It's asking for what value of k, if any, is y equals e to the negative 2x plus k e to the 4x, a solution to the differential equation y equals, sorry, y minus y double prime divided by 4 equals 5e to the 4x. So the way that we do this is going to be the same as the others at first, where we're going to take this solution, our possible solution, and find the second derivative of it. Because we need to have the two derivatives to be able to plug that y double prime in. By the way, if you ever get a problem that just has one prime, you don't need to find the double prime. You just need to find the second derivative. You just need to find the terms that you need to use given the solution will allow you to figure out if your solution satisfies the initial. All right, so let's do this. Y prime equals negative 2 e to the negative 2x plus 4k e to the 4x. Take that again. It's going to be 4e to the 2 of negative 2x plus 16k e to the 4x. All right, now let's plug that in. So we're going to get e to negative 2x, so plugging that y there, plus 4 plus k e to the 4x minus this. So 4e to the negative 2x plus 16k e to the 4x divided by 4 is equal to 5e to the 4x. All right, and so now that we've set this equal, we are saying, like, the question is asking what value of k will make this thingamabob here a solution to this. Like, which one will make it work? If there was no such value of k when we solve this, k would have no solution. But we're basically just going to solve this equation for k now to figure out which one, which, you know what I'm saying. Anyway, okay. So, first things first, this divided by 4 thing here, or sorry, this 1/4 here is really easy to get rid of because it will just cancel out those coefficients. So, we'll also very conveniently be able to x plus k e to the negative 2x, 4k e to 4x equals 5 e to 4x. Okay, you might notice now that we can combine like terms because this minus that will cancel out. So now we're going to have k e to the 4x plus 4k e to the 4x. And because these two terms have the same term here, k e to the 4x and k e to the 4x, we can add them together to get 5. Oh, sorry, not 5. I just realized it should be negative 4k there. So k e to the 4x minus 4k e to the 4x is going to give us a negative 3 because this really has a coefficient of 1 at the front. So 1 minus 4 is equal to negative 3 k e to the 4x. Remember, we can combine these terms because they have the same term here. And that's going to be equal to 5e to the 4x. Now, you also might notice that we can cancel out that e to the 4x on both sides because both, there's only one term on each side and they both include 4e, e to the 4x. So now we have 3k equals negative 3k equals 5. We can just easily solve for 5. So 5 thirds, negative 5 thirds. And that is our answer. All right. So that should finish up those. We're going to move into slope fields now, which, because we're still in the introduction to differential equations, where in the last part we were just talking about how we can prove that a solution satisfies a differential equation, where now slope fields are going to give us a way to visualize a differential equation without necessarily forcing us to solve it. The definition of a slope field is a graphical approach to solve a differential equation. Differential, sorry. So basically what's going to happen with a slope field is you are going to plot out or draw a tiny little slope of a linear line. So basically imagine just your average linear function. This is y equals x right here. It's a parent function. You're going to draw out a mini little linear line that demonstrates the slope at that point, that tangent slope, for every single point that is asked of you. So this sounds really weird at first, but it makes more sense when you just put pen to paper. So we're given a differential equation here. We know this because we have a derivative and we have variables. But this is telling us that dy over dx, our slope, remember derivative slope, is equal to x plus 1. So this means, like how we covered in the first semester, that at any point, as long as we plug in our x value, our slope is equal to x plus 1. So that means that when we're going to be plugging it in, if we use this equation, we can find the slope at any point, and from there we can use that slope to draw a linear line that has the slope that we found, and put it on put it as a little point on this graph. And I'll start doing that now. Normally, you will have x and y both in here. I'll talk more about how those two variables will look when they're represented inside the actual function, or the actual equation here. But right now, I'm just going. I'm mentioning this because I would normally put it on my little thing here, like that. But we don't have one. Yikes! Not yikes, but we're gonna have to skip y for now. So let's pick a point. Let's pick right here. When x is equal to 1 and y is equal to 0, but that doesn't matter, we'll plug that in to get 1 plus 1, which is equal to 2, which means that dy over dx equals 2. Our slope equals 2. Now, a linear function with a slope of 2 is going to be 1 over and 2 up to create your function. So it's going to have a much steeper slope than your average parent function, which would go through like that. Whoops. So we're going to draw a much steeper slope for that point, just like that. And we need to do this for all points on the graph, so we can move a little quicker. Also, note that because y values don't matter, because y isn't included, of course they matter, but they don't matter. They don't affect the slope. We're going to notice a pattern so that for every x value, the slope is going to be the same. Okay, why can't I draw this? The slope is going to be the same all the way up. This would happen in the opposite way if the only variable represented on the graph in the slope equation was y. But so these are all going to have the same slope because of the fact that x is the only thing changing what the slope will be. So it doesn't really matter what y is. It only matters what x is just because y isn't in this equation. And vice versa would be true if it was, say, y plus 1. Then x wouldn't matter and it would create a pattern horizontally rather than vertically. But anyway, let's just do 0. We haven't done 0. So let's do 0 comma 0. 0 plus 1 is 1. That's your parent function, your typical linear line. And that's going to be true all the way across because x is always equal to 1 across the y-axis, and the y values aren't affecting the slope. Going to move out here. 2 plus 1 is 3, so we're going to have an even steeper line. And then we're going to have 3 plus 1 for this line is equal to 4. This is going to be super steep. And now moving this way, negative 1 plus 1 is equal to 0. And a line with a slope of 0, a linear line with a slope of 0, looks like this. A horizontal line. It has no slope. Note that for a line that is undefined, where you'd get, say, 1 over 0, it's going to be vertical. But here, we're going to have a bunch of horizontal lines. It'll either be vertical or these are all going to be horizontal. And then we're going to have negative 2. So negative 2 plus 1 is negative 1. Recall that a negative linear function looks like that. So we're going to do the opposite of this. It's flipped. And then negative 3 plus 1 is negative 2. So this is just going to be a steeper decreasing line. And that's what our slope looks like. And you might notice there's a really clear pattern here. And that's because we've just drawn a bunch of little bits of graphs. Because if we were drawing the slope, if we were making a graph of the slope, we would be writing in for whatever this was, 2 plus 1. So this was 3. Our value would be equal to 3. But rather, we're just drawing little tiny bits of whatever the original function could possibly be. And because we're doing that, because we're drawing what possibly could be the initial function based upon the derivative, we basically have a little guess of what our integral is. And that's what the idea of the slope field is. It's a visual graphical way to look at what a derivative is telling you. And so if you were given a point, which you probably will be, you'll probably be told, given the, I forget what they call it, it might be later in here. Well, they might say something like passes through the point, but they'll give you a point or something. Say they give you 0, 1, which is this point here. They might ask you to draw what the function would look like if it passes through that point. And because we have all of these little lines here, we just need to follow them to figure out what our original function was, and follow them by making them parallel to the lines all around them. So we can make a little shape like that. And that will give us what our original function should be if it is crossing through that point. And you might notice that this makes a lot of sense. This is a quadratic function. And this, our slope here, is x plus 1. A quadratic function will always have a slope of x. And if you take the integral of x plus 1, you're going to get x squared plus x plus c. Because if you take the derivative of that, you'd get that. Makes a lot of sense, right? Why we would have a quadratic and why it would look like that. Pretty cool. So that's how fields work. Let's get into a little bit more practice over here. So one of the most common questions we're going to see is matching slope fields with different options, or sorry, with different equations, matching the differential equation or the slope with the field. So you might notice here, or you might recall what I was saying about y's and x's. If a y or an x is not, or if the slope, if the differential equation only includes one x or one y and excludes the other variable, there's going to be some symmetry going across. Like you can notice here, all of these slopes are the same. And that's because all of it was only dependent on the x value here. So it's really easy to be able to say that that must be a because of that. And you can confirm this by just plugging in values again. You look at 0, comma 0, that's 0. And if you plug in a 0 for x, that's going to be 0. But if you also do 0, comma 1, 0, comma 2, 0, comma 3, those are all horizontal and equal to 0. And if you plugged in 0, comma 1, 0, comma 2, 0, comma 3 into this equation, you would get 0 for each of those answers. So that's a way that we can confirm that there. You might notice there's also some symmetry going on here, but rather in this time it's horizontal. And that will give us a hint that for every y value, the y is the only thing that matters. The x will not affect the slope. And that's why it's really easy to cross these off quickly. Why we can say very quickly that 19 must be C. Now we get into this funky junk, whatever's going on in these things where, oh, actually, I just realized these both have a thingamabob. I've spoken too soon with whatever I was saying. Oh yeah, I didn't realize there's another X up here. Whoopsie daisy. Though I don't know why I'm erasing that. I did confirm that that must be that because of this, but that's what you're going to have to do. If you run into a situation where you have two things that could be true, you're going to have to just plug and chug. So for this one, you can see that the origin is -1. It has a slope of -1. So 0, comma 0 has a slope of -1. We plug in a 0 into here, you're going to cross out that 5 and get a -1. And that's just a way we can confirm that that looks like that. Last but not least, negative x over y is a function that occurs a lot in Can I talk? Hello. You'll just see this one a lot because it makes this fun little circle shape. And I think teachers like to use it because it has these, they didn't draw vertical lines because we don't know if they're vertical. They could be vertical or they could not exist. I think because they demonstrate every single type of slope, teachers like them. But this one is just a plug and chug situation. So say we have a 1, comma 1 right there. And that's obviously a -1 slope, or at least a negative slope. And if you do plug in 1 and 1, you're going to get -1 over 1, which is negative. So it's pretty easy to determine these once you know what you're doing with slope fields.